Okay, good afternoon, everyone. Again, it's my pleasure to introduce Georg Martius from Tubingen this week. So Georg is actually a friend of mine from Göttingen from our PhD time. So it's really nice to have him here. So Georg is leading the research group on autonomous learning at the Max Planck Institute for Intelligent Systems in Tubingen, Germany. Before joining MPI in Tubingen, he was a postdoc fellow at the IST, Austria, and was a postdoctoral researcher at the Max Planck Institute for Mathematics and Sciences in Leipzig. He received his PhD from the University of Göttingen, from the beautiful University of Göttingen, let me emphasize, and his computer science degree is from the University of Leipzig. His research focuses on machine learning for robotics, including internal model learning, reinforcement learning, intrinsic motivations, representation learning, differentiable reasoning, and haptics. And today he will talk about the differentiable reasoning parts. So it's nice to have you here, Georg, with us, and the screen is yours.
Thanks, Sinan, for the nice introduction. Thanks for having me here. Great. Yeah, I'm Georg Martius, and today I will talk about Blackbox differentiation, which is a method to empower deep networks with combinatorial algorithms. Okay, so let's start. Clearly, we have seen a lot of success stories in machine learning recently. For instance, in computer vision, we can nowadays not only recognize objects, but we can also localize them and track them through time. Yeah, this is kind of a video which I unfold through to the Zoom. Let me just sort of play. Clearly, things are happening here, a lot of objects, real world situation, and the accuracy of our algorithms are astonishingly high. Likewise, in natural language processing, well, we have now tools that can translate text to astonishingly good quality. And so all data driven, that's really cool. And clearly we also have seen recent successes in robotics, in hand manipulation, also data driven. It takes very long, but we can learn it, and also breakthroughs in computer games like beating professional Go players, or computer games like Dota and StarCraft have been tackled. Okay, that is really, really exciting. What about algorithmic reasoning? So if you think about problems that involve a little bit more than sort of an simple input-output relationship as a kind of a simple function, but something that is really more like we would write a complicated algorithm for, something like a traveling salesman problem, right? Where we want to visit all the cities, for instance, in Europe here, major cities, and we want to visit them in a tour that is the shortest and never visit a city twice. Or that think of the shortest path problem. So this is now away from the Max Planck Institute in Tubingen to the train station by bike, and we would like to know where to go. Clearly, we have very good algorithms like this, like a navigation algorithm, shortest path planning. Similarly, graph matching problem, give me two graphs, for instance, employees or like certain kind of matching problems. And I want to now find the correspondence between two sets, right? And I want to find this optimally. So in this way, I can employ a graph matching algorithm and solve these problems. So we have really, really good algorithms on the side. And we have very fast implementations, even for very complicated problems like traveling salesman, which is in principle NP hard. We can still solve very complicated instances by now. But these algorithms clearly need the perfect input specification. I need the graph, for instance, or the exact definition of what I want to solve the traveling salesman or the shortest path problem on. And if I take a neural network really just on these problems, they're really not good at these by themselves. So what about doing this, but on raw input, right? So we would like to, for instance, as a future potential application, we would like to solve the shortest path problem on images. So this is maybe a train station, and we want to go from the bottom here to the platform, so entrance on the -2nd floor to the platform number 12 here. So we would go through that map here to the elevator or to the stairs and so on to navigate ourselves to the platform. Or another interesting problem might be that we have pairs of images and we want to find how they relate to each other. So for instance, we want to find where is the nose or the eye or the ears of the cat on the left image, where is it on the right? What is sort of also a left, the corresponding eye and ear and so on. And so neural networks are really, really great at extracting the raw information, the raw data extracting information from the raw data, but they're not necessarily good at solving this combinatorial problem behind. So that's why we want to do the following. We want to build a bridge between these two worlds, essentially, right? So on the one side, we have this combinatorial reasoning, combinatorial optimization problem, and on the other side, we have deep learning. And let's make a bridge, and let's make a nice bridge, okay? So now, so this is sort of the mission of this project that we had. So really combine these two worlds and make combinatorial problems be embeddable into a deep learning architecture in a nice way. So in order to understand how this can work and what are the problems, let's look at the typical setup that we have when we train a deep network. So normal end-to-end training, we have some input, for instance, an image. We have a couple of layers, which are somehow split here for a good reason you will see later into several parts. And at the end, we have some kind of loss. For instance, the distance between a target image and the between a target output and the true output. And now what we do, right, we train all these weights of all these intermediate layers clearly, and we, let's say, do a gradient descent on with our favorite optimizer, and that will lead us to the typical mathematical description of this as a gradient descent, where we take our derivatives of our loss partial with respect to, for instance, the intermediate output, then the intermediate output with respect to the earlier intermediate output W, and so on, until we are somewhere, for instance, here in this earlier layers, and we get now how we change our weights according to the gradient descent on this loss, namely by backpropagating the loss all the way through here. Okay, clearly you guys all know this, but I just wanted to flash this out to you that we are on the same page. And now comes the interesting part. We swap out this middle part and plug in this Blackbox combinatorial solver. You will see in a moment what I really mean by this. But the interesting part now is that we have our input image. It has some kind of representation learning. This can be processed by such an algorithm in a way. The algorithm proposes a solution, and this can be processed by further layers. And then at some point, I have my loss. Okay, so as an example, input would be, for instance, a map image. Yeah? Then on this map, I define a certain kind of a grid, and the costs of each of these vertices or edges on this grid here are computed by this deep network. So the deep network takes the raw image in and spits out here a cost for each of these little grid cells. How difficult would it be to go along this line? Of course, it doesn't know this, right? This is just it spits out whatever number. Then I take this representation of this graph, right? It's a graph with a lot of vertices and costs through Dijkstra, shortest path solver, right? And this Dijkstra will output a matrix of the shortest path in this. So it would be this kind of 0-1 matrix. And then I have in my data set, clearly I have some, so it's supervised learning, I get true paths. So I get, for instance, that the shortest path on this particular map would look like this. So it's easier to go on the gravel or dirt than on to swim through this water, or to go over stones or something. And clearly this has to be learned from the data. What is easy and what is hard to traverse. And the interesting part now is clearly that we want to learn these weights. We want to learn the weights that are in this network. And well, you've seen on the previous slide, we need to do this backpropagation. So we need to differentiate this discrete solver. Okay, so maybe before we start, let me just tell you what I mean by this solver. I consider this particular class of solvers, namely algorithms, if you want, they take a continuous input and produce a discrete output. So they are mapping from this W, let's say the weights of this graph, and map this to a particular instance, for instance, a particular path, the shortest path, namely defined by this arc min here. So it minimizes over all possible paths, if you want, and it takes those which the one with the particular minimal cost. And our setup is here so that this cost is a linear cost. So in this case, weighting times which path I take, but subject to arbitrary constraints. Maybe this sounds a bit restrictive to you that we have this linear cost, but in fact, there are tons of classical algorithms that are already part of this class of problems. So for instance, the shortest path that I just described you, or approximations I start with, quadratic assignment, min-cost perfect matching, traveling salesman, a lot of stuff. Integer programs and so on. So let's continue. Now let's go a little bit deeper and try to understand how we can do this. So we really need this intermediate part, and I split this up here into this part that you really see. It's really only about this middle block. We need to differentiate or define a backward path. Wait, one second. We need to define a backward path that takes some gradient information that is here. Namely, we have our loss. We go through all these layers. We are here. This tells me how much would I need to change my output in order to be better at the loss. And I want to translate this into how much do I need to change my input in order to be better at my loss. And now we just simplify this for the moment that the loss just comes directly here. But the beauty of our method is that it just works everywhere. So we really only to look at this local linearization. And so we really need to solve this problem. Okay. Now, the good news, gradient exists, but it's completely useless. Clearly, I can differentiate the thing, this problem there, but if you just think about it, right, a small change in the input, for instance, in the weight of the graph, would typically not change, make zero change to the output. So the optimal path will not change if I just make one little node a little bit more expensive. But if I make it, it becomes higher, like more expensive, suddenly the shortest path might change drastically. So the loss function is literally a piecewise constant function with respect to these inputs of my solver. And this is, of course, not very good for any kind of gradient-based optimization because it doesn't know where to go on these plateaus. Okay, so now let's look at this. So we have our piecewise constant function. So this is a loss function, and here is our input weight W. And what we want to do is we want to create a surrogate loss, which has particular properties, which is such that we can just use that surrogate loss and we'll find the minimum and minimize that. And our surrogate loss function is, these are linear interpolations between these plateaus. They are tight, so they wouldn't go far away. So we have in the paper some mathematical description of what we really mean by this, so how close you want to be. It also wouldn't change the global minimum, that would never be changed, but local minima might, also local plateaus, they might be completely disappear like this one. Okay, so we have such an idea that we would like to compute such a surrogate loss, which is the only real thing that you can do, right? You can't really, it's not really an estimation problem of the gradient because the gradient is zero. So if you estimate it perfectly, you would get zero. So you really have to do something about it, right? So, and now what we can do is interesting. We can compute the gradient of this perturbed, of this new function, L lambda here, in the following way. We take a change in our loss, so we move essentially our W's. Then we solve this again. We solve our solver, we make another solution. And this perturbation is actually exactly given by the derivative of my loss with respect to the output. So here is one hyperparameter lambda, which tells me how far do I want to perturb my input. I make one more solution to my problem solver, to my problem. Maybe this changes the solution. And then I get the gradient as the difference between these two and the shifted solution. And so this is the super simple formula that comes out. So I take my output that I had before minus my output that I had after the perturbation, and then I have this hyperparameter lambda that I used here, and that's it. And the cool thing is that this is really the exact gradient for this approximation, and I only need to call the solver exactly one more time. So in forward path I would need to solve my problem, and the backward path I also would need to solve the problem once on a new instance. And this exploits the fact that my cost function is this linear function. Okay, so what comes out is I have my original loss, which is piecewise constant, and now with this lambda parameter, I can interpolate it to become smoother and smoother. You see here the large plateaus are still there, but the sharp boundaries already disappeared. And then if I crank up that smoothing, essentially, then the landscape becomes more and more smooth. And of course, this is now here something that the algorithm is only implicitly computing. You never really compute this entire loss landscape. You only get it at a certain point. But here for visualization, we just sort of ask it to compute it everywhere. Cool. By the way, if there are questions, please just interrupt. Yeah. Okay, so what is pretty cool about it? It's very efficient because of this exactly only one extra call. It's theoretically sound, so we give in the paper some different variations of this linear interpolation, and we can show that this is sort of well behaved, and it's super simple to implement. I will later show a piece of code sort of to see how simple that really is. Okay, but before, I would like to show you a little bit some examples how this works. So as a proof of concept in our first paper, this was this iClear 2020 paper that we introduced the method. We have been looking at a couple of different problems. So one is this shortest path problem that I was just talking about now as an illustrative example, and we will look at it now. So the input to this system are these maps. These are actually World of Warcraft maps that we generated ourselves from the tiles. That was great fun to have a big data set, which is also now public. And we have for a couple of levels, we get or a couple of these maps, we give the shortest path. Then we train it as I told you before. And then at runtime, I give it new maps that I haven't seen. Okay, and now depending on the size of the map, here is the performance. So the yellow curve is a ResNet that would just try to train this end-to-end. And just as a side note, the ResNet is 100% accuracy on the training set, right? We managed to train it and it can memorize it. So it has enough capacity to essentially solve the task in terms of its capacity memorization. But when I ask it to generalize, it will fail terribly. So so this is the performance of finding the correct shortest path on this, and this goes essentially to 0. Whereas with our embedding, we are very close to 100%. And some of these instances are maybe also, yeah. So in very few instances, we make small mistakes, but otherwise we are perfectly generalizing. Cool. Now, a second interesting example is this traveling salesman problem. So let me explain a little bit how that works. So we came up with this little funny task. So imagine I give you as an input the flags of countries on the globe, and I say that I want the shortest path, the traveling salesman tour, between the capitals of these countries that I give you. Okay, so the algorithm does not know clearly what does that mean. It just gets pictures, but it has to sort of associate with this picture a coordinate on a 3D sphere. So this is what we did. We say, okay, we live on a 3D sphere. On a sphere in 3D, clearly the world, and you have to sort of predict the position of this potential city, and then we use that to run simply the position of all these cities through a traveling salesman solver. Could Roby here, highly optimized C code, and we run it, and then the output is then compared to the true one. So here is a video that I will maybe show it a few times, how these cities are essentially moving on the planet, on this map. And at the end of the training, when we do this over all these little pairs of always like 10 cities or so, the algorithm really finds and puts them in the right place up to, of course, rotation on the sphere. But so this is extremely remarkable. I think the distance between the position on the map and the true position of the city that we found is in the order of 20 kilometers or something. It's ridiculously close. And so that's pretty cool. So again, I start with input flags. The flags are so I learn an input representation for my solver, which is the position of these cities on the globe. Then I run it through the solver, and then I check for the true one. And again, I have a held out set of tors, which I don't touch. And here is again the plot. Now in this light color, you see the training performance, which I removed in the other one. So here you see the ResNet can also again solve it for training time, but at test time, it is also terribly bad. And again, we even generalized to tors with 40 lengths, which is really a complicated traveling salesman problem already, and relatively, and it can solve this just from these images. Clearly, the solvers nowadays can solve much more complicated instances.
Sorry, Georg, there's a question in the chat.
Yeah, yes, okay. The problem is I can't see the chat on my computer, so maybe now, because I have full screen on, so maybe if you could read it.
Have you not observed any drop-off in generalization accuracy with increased map sizes?
This was to the previous one, right? I mean, the beauty of it is really that what is learned is, one second, I will be there. Essentially, what the deep network learns is to associate every tile or every local part of the image with a cost, right? And this is super generic, right? Once you have learned this, it doesn't matter how big the map is, because your Dijkstra algorithm will anyway solve it. Even if it's 100 by 100, it will just solve it. And so in a way, this generalization is really built in and very strong, right? Because you say, okay, we know what you have to solve. It's a shortest path problem. We don't know the input representation. Please learn it. And then we do it. So we only looked at this 30 by 30. And probably if you go up at some point, you will just not get the perfect accuracy. You will just get a slightly different path. That's clear. But yeah, so in what we have observed so far, it wouldn't die great. But I can imagine that it could if you crank it up. In particular, if you haven't seen maybe parts, if you have never seen parts like new textures or something, then you cannot generalize, right? So you need to, of course, learn the right input representation. But this is standard deep learning problems, right? Does it answer your question?
I think yes. Yeah. Yes.
Okay, let me show you this video one more time. So you started at the beginning, you see where the cities are just somewhere on the globe, and then they slowly move. I don't know whether you can see this with Zoom. It's probably a bit cranky. I will show this one more time. They start at the beginning somewhere, and then they move around. At some point, they slowly converge to the place, and then they go finer and finer. Cool. Okay, so this is that. Now let's come to some actual applications. So the first application that we looked at was actually in computer vision, so the real world application, which is a bit funny because you will first think, what does that have to do with this combinatorial optimization? That I will explain this to you in a moment. So they are in computer vision. There are a lot of problems where you would like to optimize, or you would actually evaluate your problem, your network, using rank-based functions. So for instance, mean average precision or a certain recall is typically defined in terms of a ranking. And it would be great if you could just directly optimize for this metric, because then your network is really doing what you wanted to do and not some surrogate loss that you would maybe otherwise use. So the idea was maybe we can use our technique to make ranking-based losses easily differentiable. Okay, so right, these ranking are popular in problems for object retrieval and localization and so on. And so how does that work? I have a network, right, that takes an image and spits out a score. y. And then a ranking is simply the permutation of that score that sorts it, right? So let's say I have these scores 1, 2, and so on and so on. And then the ranking would be the order. So then it would be the order of these guys such that they are sorted, right? And so now this is a piecewise constant function, the sorting, because if I just change the score a little bit, then I would clearly not then I would clearly not change the sorting, and if I change it a bit more, then I sort it. Okay, so the direct optimization of this loss functions is difficult, right? Because I am I have this again, this piecewise constant nature. And this was clearly is interesting, and it was before we had this paper here in 2020. There were a lot of other papers that looked at this, and they were also highly received. So, for instance, papers that try to make the sorting itself differentiable, for instance, by a deep network. So, learning a deep network that would differentiate it, or people proposing this AP loss and other things. And also from Sinan and co, the paper on this rank-based balance functions was concurrent with ours, or a little bit later. We didn't know this. I mean, this was at Europe's, and we were earlier that year. So I think that came out later. But anyway, so this is also a little bit of a different direction. But there are a lot of papers that try to go on this problem. And so let's see how I show you how we solved it. So the idea is that we phrase this ranking as an optimization problem. So namely, we say, okay, we want to find a perturbation pi where the following cost is minimized, namely this cost that I have this perturbation times the score. Now you imagine if I sort them the right way and I give them the value of their rank, then if I have them in the right order, then this product would be minimal. This you can prove. And so this is just to make sure that our theory that we have before is actually applicable. So this Blackbox differentiation can just be applied because this is of this sort. Of course, if we want to do this in practice, we are not, of course, we just have to sort it, right? So our solver in this case is simply torch.argsort, if you are in torch, or like just simply sort the sorting function, the argsort function. So this is, of course, super fast. And now there is one more trick that we had to do, which is applying a margin. So now you can imagine if you have this score and you just look at the ranking, then you can have the scores very close by, and a tiny perturbation of the scores will change the rank, right? This is sort of what then would come out. So because there's no really pressure on how the scores should look like, that they maybe have a certain size or so. And so in order to resolve this problem, this kind of instability, we introduced this margin. So instead of the plain ranking where we have simply positive and negative scores now sort of next to each, we at training time, we deliberately shift them the wrong way. So the guys which should be later, so ranked higher, they are shifted to, their scores are shifted to the left, and the other way around. So and in this way, we make the gap between our positively, like the positively labeled guys to be have a good gap in the scores to the negative ones, right? So in this way, I will make sure that my scores are far apart, or at least so as far apart as needed in order to give the stability. So at training time, we deliberately move our scores around. Okay, so then here this is now a little bit of the code. So the forward pass is simply I take my input and I save my input and my ranking for the backward pass, and I just do ranking. So sort, torch.argsort. On the right side, my backward pass, I have to differentiate now through the sorter. And so I load my inputs. Then I said I perturb my scores. Here is actually this also the margin, which I left out here for clarity. But in a principle thing, I just take my this incoming gradient. How do I change my loss in order to change my how should I change my ranking in order to be better at my loss? I have this hyperparameter lambda here. I change my scores and I sort again. And then I take the difference between the two sortings, and that's it. Okay, so this is it. So it's essentially 2 lines of code. And so you have to you create a custom backward pass, but otherwise it's all super easy. And this thing we named Rambo. So in the paper, so okay, the image doesn't occur. Here it is. Anyway, just a bit of fun. And now let's look at how this works. So one task we looked at is object detection, where the score is mean, average, precision. And so here we provide consistent improvement over the classical version that you just optimize for the cross entropy on the Pascal VOC, for instance, and on other data sets. Here by really just drop in replacement to take an architecture that was there and we just drop in, make it replace the cross entropy loss by our Rambo. This is differentiable ranking, and we get consistently better scores. And then we also looked at image retrieval. So that's where you get an example image and you have to find the appropriate images in a large corpus and find the best K one. So that's why the loss is recall at K. And so there are a couple of standard data sets which we looked at. The benchmarks are a little bit problematic. This was also raised in this paper here, but so we looked at this is now for enclosed, and here is our method, which is not bold because of some funny things. So that there was some implementation which nobody could reproduce in MATLAB. But if you take all the, and we couldn't, and the authors also couldn't really reproduce in their own Python code. So it was really funny. But otherwise, if you take this away, we are on par with or better than the state of the art with a much simpler architecture. So that was pretty cool, pretty good news. I didn't follow up on this now, what actually happened. So maybe I guess people have been improving this. Okay, so now a second application is also in computer vision. This is what this key points correspondence problem that I already mentioned. So I have now as an input, I have 2 images and with key points already marked, and I want to find the correspondence. So where is the corresponding part on the left image to the right image? So on the left and on the right, we get essentially points, which we also connect to a graph. But in principle, the pure algorithm problem is I have these key points and I want to find these links. So the quadratic assignment, who of the left is associated to the right, and I can only associate one by one. I cannot associate these two, so this would not be allowed. But I first have this entire connection, and I learn what is the cost of connecting these nodes. And then I solve this, and interestingly enough, we can also enhance this problem by adding the edges between them, and also say there is a certain edge cost. And now I can say, okay, if this edge, how bad is it if this edge becomes this edge? And now this is this quadratic assignment problem. So I again want to minimize an assignment. So the V's and the E's are the edges and vertices in my final assignment that I want to do. So I go over all possible assignments if you want, and say I want to pick the one which has the smallest costs here. And clearly we don't really know these costs, right? So we have to learn them ideally. And so this is then our big architecture. We have these costs. We do a graph net that would propagate here some costs on these image patches around each of these key points. And we get costs on each vertex, or like numbers on each vertex and numbers on each edge. These numbers together are joined to create this costs, this vertex cost that I just mentioned, and even the edge costs. And then we have a solver, which is a very fancy solver. from the MPI in Saarbrücken, and they can solve this problem not only for this typical costs, the edge costs, sorry, the vertex costs, but also for this edge costs. Anyway, what I want to say is we have this input, we get at the end the output, namely whether we have the right key point correspondence, and then we backpropagate with our method through this entire procedure, and we can train everything into it. So this is really, really fancy and is quite a big architecture. But at the end, the architecture is also relatively simple for this task because it really takes standard components, plug it in and train it end to end, and we manage very well. So this is essentially a comparison to the best competitor at the time last year. And so we were able to beat it on, for instance, this S-pair data set by quite a margin. And we have in the paper a couple of other data sets we looked at. And here are some nice visuals. So here you see, for instance, some interesting correspondence problems. Here the two birds or buses or the bicycle here. The red one is wrong. So it mixed up these two, quite complicated. And here is a completely failure case, but you can imagine maybe why this fails. Good. Okay, so then maybe as a last thing that I want to tell you is that just briefly, the other thing that we are looking at, and this is sort of also very interested in the direction of my overall goal of my group, is to apply this in reinforcement learning, right? So reinforcement learning methods, they don't generalize very well to variations in the environment. And this was recently studied by this paper from OpenAI, this ProcGen paper, where they introduced a suite of networks, of problems, namely of these computer games, where there are many levels. So every time you can just play this, you get a new instance of that environment. So for instance, the maze would look every time this different, or in any of these environments here, the structure is the same, but the particular instance is different. And then they checked in this paper how many of these different levels do you need to see in order to be able to play a new level. And the kind of astonishing fact is that for, let's say, a standard PPO, which is a standard policy gradient method, you need, so this is the orange line, is the interesting one, you need about 100,000 levels, or maybe 50 to 100,000 levels, in order to do well on unseen tasks. So have a small generalization gap. And similarly on this chaser, we also need 10,000s of levels in order to be good. Chaser is this kind of Pac-Man game. And so maybe, I mean, 100,000 levels, that's a lot. Imagine you would play these games, you probably need to play 3 of them and you know how this works. But of course, we have a lot of prior knowledge, I mean, clearly. But this is not really satisfactory. And so we thought, okay, maybe this is the perfect thing. So here, these are some examples from these mazes. If we take now an policy and say the policy itself has to solve a shortest path problem inside. And again, we have to take this map. It's a little bit similar to this thing that I explained to you before, but it's a bit more complicated. You have to do time dependence because maybe something happens in the environment. For instance, here in this environment, you have enemies that come at you and they would eat you, a little bit like the ghosts in Pac-Man. And so you have to find a shortest path in a time domain, so where the enemies are coming. So you can really have very interesting paths like this one, for instance. And the network would need to predict where it needs to go next. But taking all this in and doing the typical training end to end, we are able to solve these levels, these tasks already with very few levels. Now we are 100 and 100,000 levels, and you see already after about 30 levels we can solve half of them, and then here at 1,000 levels we can solve all of them, where ProcGen needed 100,000. And similarly, also in this environment, we are quite a bit better on the low regime of it. So this is really interesting. But so far, this was an imitation learning problem. So we were given optimal paths on this, but we only had in this way one particular path per environment, whereas ProcGen has 200 million trajectories that it can collect, so it can see everything in these levels. Anyway, so this is sort of a thing that we are just doing, and we have a first paper under review on this, and we are looking how to make that even extend it to more complicated problems. Okay, so now it's time to summarize. I showed you that a large class of combinatorial problems can be embedded into deep networks. We can train them in the usual way now, sort of business as usual. There's not really anything that we have found that is a problem there. There's only one more hyperparameter, but it's also typically very easy to choose. It's not very sensitive. It's implemented in a few lines of code. We have the code, and also for the different papers and data sets are now online. And something that we want to look at next, and partially already did, is to try to learn essentially the combinatorial problem. Right? So far, we plugged in directly the problem. We said, okay, this is the shortest path problem, this is the traveling salesman problem, and so on. But it wouldn't be cool if you have just sort of a generic block, namely an integer linear program, and we learn both this input representation, so the cost type, and the constraints at the same time. And our first paper on this is just came out now and will appear at ICML 2021. CompOpNet, this is how we call it, and it learns the constraint as well as input representation. And so this is sort of the first step in towards a kind of a generic part that you put into a network, even without that you need to know exactly what happens. But I mean, to have it really general, I think there's still some way to go, but this is already a very interesting first attempt, inspired by this seminal OpNet paper. And now, second thing is this reinforcement learning. So I've shown you the first little results, but we want to take this on and see whether we can put this into more complicated setups, maybe hierarchical planning and so on, to really make agents be more successful in new environments and new tasks. And I think there are probably a lot of things we could do. We're really just at the beginning of this road. So if you have some ideas of where this could be applied, maybe have a good application or so, let us know or contact us. Okay, so that's it. I would really like to thank my fantastic team of students. So Michael Rollinek here is the person who was mainly driving the initial part of this Blackbox differentiation. And then there are many strong students that helped in this, Marin and Anselm, for instance, and Dominic. And so I'm really grateful for working with them, and thank you for your attention.
Thank you, Georg, for this nice presentation. It was really interesting for us, especially. Any questions from the audience? Okay, I have taken some notes.
Maybe I can start, Sinan.
Sure.
Thank you very much, Georg. It was really very nice presentation. I learned a lot. This might be a dumb question, but so perturbing the input and running your solver again reminds me the regular finite difference method in numerical differentiation. Can you comment on that, the relation between finite differentiation and your method?
Absolutely. So the difference is that for finite differentiation, right, you would need for every input, for every dimension of your system, so if you have 100 variables, you would need to do this 100 times, right, for every coordinate.
Right.
And in our case, we compute the perturbation direction directly with this. Let me go back to this slide. Let me see, maybe that's faster if I do this way. And so we need exactly only one pass, because we are not doing a random perturbation or like an uninformed perturbation, but we can, in this case, perturb the solver directly in the right direction. Maybe I find this here now, maybe not. Here, this one. So this perturbation here by this gradient that comes in. So this is a vector, right? As high dimensional as your output is, and the input and output dimension is the same for these solvers. So you will get essentially a direction of the W's you want to change, which is already sort of like a gradient descent. So it's a vectorial change. And so in this way, we need only this one extra call. And a recent method that came out from Google research which is called perturbed solvers. I forgot to put the reference here, but they do an approach where they randomly create these perturbations, and so then say, okay, we have a kind of a Monte Carlo sampling of this smoothing, so like a Gaussian smoothing of the loss landscape, and they do this by random sampling, and they are also relatively good, but they need then typically more calls for Monte Carlo.
I see. Okay, thank you.
Yeah, you're welcome.
Any other question? So we are doing linear approximation, linear smoothing. So would it possible to do something nonlinear?
Okay, yeah, so where does that smoothing come from? Maybe I can show you why this is sort of happening. I think maybe this comes, and then I can explain you maybe why this might be difficult to like. Okay, so the smoothing comes from the fact that I have here my loss landscape, which is sort of this piecewise constant plateaus, right? And this perturbation that I do, you can think of as like moving these plateaus along. And now you take the gradient. Do I have this picture here actually? Maybe not. Now the gradient is now connecting the green with the blue at a certain point, and that's why you get this kind of slant. And the slope or the shape of this connector is essentially exactly your cost function. So this is where the linear function comes in. And so we thought a bit about it, and I think if the problem has more nonlinear terms or something, and we could do this all, then maybe these terms would become nonlinear, but I really don't take me on this. So we're not sure about this yet. And I think if you do this kind of smoothing with this Monte Carlo estimation, so then you would get the Gaussian kind of smoothing, then we get some nonlinear thing. But in our case, that becomes automatically linear, and because of this trick that we only solved the solver one time and about this construction. Okay. Would you think that it would help to have it nonlinear? I mean,
I'm not sure as well. So it's.
I mean, you know, my intuition says a bit that our gradient descent is anyway like a linearization, right? So I mean, I take my function, do a local linearization, and do a step. So then sort of linear, I mean, anyway, linearizing my loss is kind of a good idea. So because we anyway do it, we always do small steps in this optimizers anyway. So I think that's perfectly fine.
So if you are in a very large plateau, then is it possible that after perturbation, I'm still inside the plateau and I still get
zero gradient? Yeah, so this can very well happen, and it also depends, of course, on this lambda. And maybe you say, okay, maybe then why don't I put lambda to infinity or like super high, right? And there are certain problems where this is actually true, that you can put lambda very high, where the solutions obey some kind of suboptimality, subparts. But in general, I can't do that. So I need to fix some kind of, I need to maintain some locality information. But so what is really important that we're doing stochastic gradient descent, right? So maybe in one batch, I'm landing on this plateau, but in the next batch, I'm landing on some, I mean, for the next batch, right? This thing looks different, right? And so I'm landing on some place where I get a gradient. So I start moving. So it's a little bit like if you talk about, you know, differentiating through a ReLU network. I mean, maybe you'd also think, I mean, come on, I have constantly these guys, this constant parts of my activation function that have no gradient. But then in a couple of batches, I get suddenly something for that unit, and I start to use that unit again, right? So this is very similar here. So maybe I'm on this plateau for half of the batches, but I don't really care. At some point, I get some gradient information, and I will start to move around, and then my loss landscape changes.
Okay, I think that makes sense. Any other question? Otherwise, I have a lot of points.
So maybe I can again ask a naive question. So the very simple way to make these possibly differentiable is like coming up with approximations where y is continuous.
Yeah, so relaxations, right?
Yeah, relaxations, yes.
Okay, so this is clearly a possibility. And our standpoint was that for really hard combinatorial problems, like say like the traveling salesman problem or so, these relaxations are not terribly good. I mean, there are a large class of problems where this generalization is where this is okay. and others where it's not. So sorting is relatively easy combinatorially, of course, but still somehow the relaxations are not as good and it's not so easy to implement this, but for many problems we found that the relaxation would just not be good ready, so we have to do compromises on the combinatorial side, and we said no, we don't want. So we wanted to use the optimal C implementation or whatever implementation you get for your problem, which are really strong, and there's a really huge gap between a naive implementation of these solvers and the state-of-the-art Gurobi or even specialized solver for particular tasks. So that was sort of our motivation. But clearly, for a certain application, if you have a good relaxation at hand and it works well, then go ahead. But also sometimes this relaxation doesn't mean that you have a good gradient, right? So yeah, the solver itself might be a very complicated program that arrives at this relaxation, and then you have to backpropagate through that entire problem. And maybe this implementation is not even, like, as you said, I don't even have it in Torch in automatic differentiation, but maybe I have it in some external library. So there are this kind of caveats of this, but it might be, it's possible, it's legitimate in cases.
Okay, thank you.
So can you comment on neural Turing machines or pointer networks, which are trying to directly solve the optimization problem, this combinatorial optimization problem? So I guess they're still not able to compete with this level of performance, but
okay, I mean, I know the differential neural computer or neural Turing machines quite well, but okay, we haven't really tried to compare them because somehow they really try to solve the problem from the other end, really to sort of try to learn the combinatorial problem and not use a solver. But okay, I mean, that's clearly a good idea. These differential neural computers are really not easy to train. I don't know whether you guys have tried it. They are really beasts. But and I think the algorithm that they have been able to train or like to learn so far are relatively simple, right? So like a large traveling salesman problem, they wouldn't really learn so far. But they are super interesting, and this is sort of an interesting route into this program synthesis or like really trying to learn the algorithm that describes data. I found this super fascinating. Maybe it would be interesting to compare this. But I guess it's a bit of an unfair comparison because we already put so much structure in our network, right? That sort of it's more like an upper. It's for certain problems, it's more like an upper bound what you can achieve with such a system. If our assumption is correct that this particular problem is such an optimization problem with this structure. So
I guess they are not able to cope with image level data, image level complexity. So and maybe you can, so you have the inputs and the outputs of your black box differentiable box component. So you can maybe use that as a teacher network to better guide the neural Turing machine.
Yeah, that'd be interesting. Yeah. Or I also didn't really think about memory really. I mean, this neural Turing machines was strong at them, and also this pointer networks and so on. If you want, that they have this memory structure that they can use, right, to then operate on it. And they typically do the smoothing, right? They do the smooth memory, like an attention type of mechanism, which allows them to differentiate through this. But maybe this mechanism itself could also be, I don't know, because I think this is a bit of a problem there, that everything is so smoothed out that these algorithms, they won't really converge to the crisp algorithm because it's very long, everything is very smoothed out, and so they can't really, find the true solution. Who knows?
They cannot control the network at that level, but with your method, maybe you can provide additional losses at that level, like a teacher-student network. I'm not sure.
Sounds interesting.
Okay, if there are no other questions.
Maybe I have one more.
Sure.
Sorry, if you have time.
No, go ahead, clearly.
So I was thinking also about nonlinear approximations. Could it be a little bit like variation of inference and a little bit like, I don't know, I'm not sure how relevant, but proximal gradient. Would it be possible to fit continuously approximations to the actual combinatorial problem that you have? Like, I forgot it's like RK. So can it be possible to come up with like local approximations where the approximator itself is something that you train along the way?
So
like,
I think this, yeah, I see. So this, for instance, is this. Wait, let me just go to this slide. So this, for instance, for this differentiable ranking, this is, for instance, the approach that this so deep operator is doing. So it trains a network that would mimic the solver on the forward pass, okay, and then it would sort of differentiate through that network on the backward pass. And so this is possible, but this so deep, so this gradient that you get there are often pretty misbehaved. So we have, I think, we made a plot for the so deep, what is called gradient for the sorting, and it's dreadful. It looks very rugged, and it doesn't really give you a nice smooth descent, and it's super slow. But I don't know. I mean, I wouldn't say that this is kind of a dead end or so. I think this is also very well possible to do something there. But was it really your question? You started with this nonlinear approximation. Did you mean nonlinear costs also, or I didn't really know what you were referring to?
It also I think what I have in mind also comes with relaxation. It has to involve some kind of relaxation, I guess, but otherwise it's not very clear. I was thinking like I have my y's perhaps in relaxed world, relaxed y's, and then I have my approximator, and it possibly checks how well it correlates with the actual, but not completely clear how to formulate it. I guess I need to write down the equations to make it more clear.
So I could imagine that you could also now use a very similar methodology to differentiate through this relaxed version, but in a very efficient way. So not actually trying to differentiate through the relaxed algorithm, but also doing this kind of quasi-linearization or black box gradient through this. And then you have a continuous to continuous mapping, which is also interesting. So our mapping is now continuous to discrete, and maybe there are even some problems where you have this continuous to discontinuous output, like a quadratic program. So this is like what the OpNet paper is solving. So they have this setup, but the input and output is both continuous. And we found that mostly for these problems, or like this is a little bit of intuition, but so that for these problems, the relaxations or like the normal neural network fit is actually sort of okay often. And for these combinatorial problems where they have integer solutions, they are really much harder in a way to just imitate by a neural network. And then the coolest thing would be now to go from somehow discrete to discrete, something like a SAT solver or something. I don't know. Cool.
Okay. I think there are no other questions. We can thank the speaker again. So maybe we can have a virtual applause. Here, Georg, it was a really nice talk, interesting ideas.
Thanks a lot for having me.
Yeah, we'll be in touch with the upcoming papers and maybe a presentation to the group.
Yeah, this would be really good.
Okay. Okay. Have a nice weekend, everyone.
Yeah, thanks, and everybody.
Thank you again.
Thank you very much.
Thank you.